Okay, so thanks everyone for coming back for the second lecture. So yesterday I introduced some probabilistic notions of Kolmogorov complexity. And the goal for today is to show some connections to cryptography and complexity theory. So in more detail, so the goal for this talk is to look at some of the major open problems in complexity theory, such as the relation between NP and BPP, which is a question about the worst case easiness or hardness of NP. We can also consider the average case complexity of NP and the existence of one-way functions. So these are pretty much the most important questions in complexity, from like P versus NP up to cryptography. And what we're going to see today is that all these basic questions, they can be restated. They are equivalent to questions about time-bounded Kolmogorov complexity. Okay? And the results that I'm going to present, they're based on joint work with Shuichi, Rahul, Jinjian, and Mikito. Okay, so what do I mean by equivalences to questions in Kolmogorov complexity? So we will be looking at the major principles in algorithmic information theory, such as the symmetry of information, coding, which I talked about yesterday, and also variants of language compression. And we are interested in the following question. When these key principles from the time-unbounded theory, when do they survive in the time-bounded setting? And there's a paper of Levin explaining that some of these questions, they were considered even before the statement of the P versus NP problem. And in particular, it was already of interest in the 60s whether the original proof of symmetry of information, which uses an exponential search, whether it could also be done in the polynomial time regime. So in other words, whether symmetry of information holds in the time-bounded setting. Okay, so some of these are very old questions. And as I mentioned, we're going to see that whether these principles or some variants of them survive or not in the time-bounded setting, this is equivalent to the major open problems from complexity theory. Okay, so here's a table summarizing our results. So on the left-hand side, we have the three problems, one-way functions, which is essentially capturing the existence of cryptography, the worst case easiness of NP, and the average case easiness of NP. And we will see that these assumptions, they are equivalent to all these bullets, so all these statements are equivalent. And in particular, we will relate the assumptions to like coding, language compression, and symmetry of information. And one thing I would like to highlight from this table is that while we have a pretty good understanding of the role of symmetry of information and its connection to one-way functions, this is missing in the other two cases. Okay, so in the other two cases, we do have equivalences to variants of coding and language compression, but our understanding of the role of symmetry of information is still open. So we have implications in one direction only. All right, so one-way functions will give us the most complete picture about the relations to the other principles. And that's what we're going to focus on today. And this also is going to cover most of the techniques used to establish other equivalences. Okay, so we'll be looking at symmetry of information and one-way functions. So a quick recap. So Kolmogorov complexity of a string is just the minimum length of a program that recovers the string. That's the informal definition. In the formal definition, we fix a universal machine. And we define the complexity with respect to that machine, as we saw yesterday. We can also consider the conditional Kolmogorov complexity of a string x given y. And this time we give y as part of the input to the universal machine. That's just the standard definition. And we also look at the time-bounded versions in different talks. Just to remind you of this notation, so k superscript t is when we fix this time-bound t, and we look at the minimum description that runs in time at most t. Okay, so that's k superscript t. And now let's talk about SOI. Valentin has already explained it in the previous talk. So one direction of symmetry of information is the simple one, saying if you want to encode a pair of strings x and y, then what you can do is you take the best description of x, the most economical description, and then you consider the best description of y if you already have x. Okay, so that's one way you could encode the pair x and y. And the SOI principle is a theorem saying that for every pair of strings x and y, you can do much better than this. Okay, so the Kolmogorov complexity of the pair is at least k of x plus k of y given x. And that's the non-trivial direction of the theorem. So if you now put together the two inequalities and you look at kxy and also kyx, so you get this further equivalences here. And now if we just reorganize these equations, we get k of x minus k of x given y equals k of y minus k of y given x. And if you think about these two quantities as the mutual information between x and y, so this is precisely the equation that we have for mutual information in Shannon's information theory. Okay, so it's similar. It's a similar equation, and that's something we're going to be discussing later today up at 6. These connections and these intuitions from the Shannon's theory and the algorithmic information theory. So symmetry of information is one of the examples here.
But if you have just the one, the previous one,
this one,
it's not obvious how to get this.
Yeah, it's not obvious.
And this in the relation has no clear.
At least it's not clear to me. Yeah, that's a very good point. Yeah, yeah. So for this talk, when I say symmetry of information, I'll mean this equation here. Yes, thank you. Okay, so that's in the time unbounded regime, and SOI has many applications. It's one of the central properties of Kolmogorov complexity. And in this lecture, we're interested in the question whether it survives in the time-bounded setting. So we fix the time-bounded measure k superscript t, for instance, and is it the case now that for every pair of strings x and y, the interesting part of the equation is still true? Okay, and we, because we are in the time-bounded setting, we allow some slack here, so we allow some overhead in the running time, which can only decrease these quantities, and we also subtract some log term. Okay, so the question is, can we establish such equation, such inequality, for every pair of strings x and y? So any questions so far? Okay, so we're interested in the existence of SOI in the time-bounded setting. And we will be discussing the connection to cryptography and to one-way functions. So just how many of you have heard about one-way functions before? Okay, so not everyone. So here's the definition. So for a function f computable in polynomial time, and we're going to assume it maps n bits to n bits, we say f is a one-way function if every efficient procedure that can be probabilistic fails to invert f on a given input x. So we sample a random x, we give f of x to the algorithm, and the probability that the algorithm succeeds in finding a pre-image of f of x is tiny. Okay, it's subpolynomial. So in other words, a function is one way if no algorithm is able to invert the function with non-trivial probability. Okay, so given f of x, reconstructing x is a difficult task, or some pre-image of f of x. And one-way functions are really the central object of study in cryptography. So they are necessary and sufficient for many of the basic cryptographic tasks. And whether one-way functions exist or not, it's a major question. Okay, so we cannot establish this unconditionally, although it's widely believed that many candidate functions are one-way functions. Okay, so many years ago, in 95, Longpre and Watanabe, they established the first connection between one-way functions and symmetry of information. They proved that if indeed we have one-way functions, then the symmetry of information inequality doesn't hold for KT. Okay? I'm going to go again briefly over this proof because I'm going to mention some modifications to the proof later. Okay? And it's also a good way of practicing the symmetry of information inequality. Okay, so what we would like to show is that the contrapositive here. So if we have symmetry of information, then we're going to break any candidate one-way function. Okay? So we have this candidate function mapping n bits to n bits. And for simplicity, I'm going to assume that this function is injective. Okay, so this is going to simplify the proof a little bit. So I have an injective function. And I'm going to take some time-bound t that is sufficiently large, some large enough polynomial. And I'll take a t that is larger than the complexity of computing f. Okay, so these are just some assumptions that will help us with the proof. Okay, so that's the setting. And now we want to invert the function. So we are given some f of x, and we want to recover a pre-image. In our case, the pre-image is unique by this assumption. So for this reason, we'll be interested in this quantity, k of x and f of x. And you should think of this as the string y in the symmetry of information inequality. So let's just now apply the inequality. So it says that for a given t, this quantity is at least k with some overhead, poly t, of f of x plus, and now we have x given the second string. And there's some gap here. It's going to be logarithmic in t. So let's assume t is some polynomial. Yeah, so t is some large enough polynomial, and then this is going to be log t. Yeah. Yeah, because t is poly n, so then we get log t. Yes, thank you. Okay, so that's the inequality. And we would like to recover x from f of x. So we're interested in this term of the inequality. Okay, so let's just rewrite it. So now this is at most this quantity here. Okay, so that's just rewriting the inequality. And now let's try to understand these two terms. So this one contains x and f of x. But of course, if we have a description of x, then we can also get f of x by just applying f to it. Okay? So this quantity here is going to be at most, say, kt over 2 of x. Because I can take the description in time t over 2 of x, and then I apply f. Maybe I spend another t over 2 time, and then I get kt of x and f of x. And here I use the assumption that t is large enough, so I can compute f and get an overhead of at most t over 2. Okay, so we get this minus all right, so we have now simplified the inequality, and we get k t of, roughly t of x minus k poly t f of x, and some small order term. And now we're trying to invert the function, so we only need to succeed on a random x. We don't have to do it for every x. Okay? And if you take a random x, then we know that even its time-unbounded Kolmogorov complexity is very close to n. And because f is a permutation, is an injective function, this is also a completely random string, so this is also very close to n. So these two quantities, up to, say, log n, they are the same. And we get that for a random x, this quantity here is at most log n. Okay, now we have that there is a program of length at most log n that recovers x from f of x, and it runs in polynomial time. Okay, so if we try our strings of length roughly log n, we can recover the pre-image. So and this entire thing is in polynomial time. Okay, so that's covers the main idea for the proof. The general case requires a slightly more complicated argument. Okay, and that's the result of Longpré and Watanabe. And that shows one direction of the inequality. And what they asked in 95 is the following: can we show converse now? So can we establish an equivalence between one-way functions and symmetry of information? And this is, in the original way they formulated, this is still open. And what we're going to do is we're going to establish an equivalence for a variant of symmetry of information. Okay? Now let me give you an intuition for why it's useful to introduce a variant of SOI. So if you look at the statement of one-way functions, there are two important. Say again? Oh yeah, sure. Which one is this now? Do you know? Yeah, thank you. Okay, so if you look at the definition of one-way function, you see we're talking about probabilistic algorithms, and we only need to invert the function with some success probability. So very naturally, this hints at the possibility of also taking into account average case complexity and probabilistic notions of Kolmogorov complexity to obtain this equivalence. Okay, and that's what we're going to do. Any questions so far?
No, but if you take average pairs, they are somehow independent, so it's not exactly average.
So if you take a distribution over pairs, okay, maybe I'll give you some intuition. If you look at this proof,
just a arbitrary distribution.
If you look at this proof, so we are interested in the pair x f of x, which is the sampleable distribution of pairs, right? And we're only trying to recover x from f of x for most or for a fraction of x's. So if you had just an average case version of symmetry of information, this would be enough for this proof. Like if you had SOI for most pairs, then you'll still be able to recover most pre-images. So you see, you can already relax this direction of the equation to like SOI holding for like most pairs or for a decent fraction of the pairs. And similarly, if you had here a different notion, if you had, for instance, PK, you could still perform the search, but you would need randomness. But that's fine because when we're talking about breaking one-way functions, we can use randomized procedures. So one direction can be extended for average case and for probabilistic notions. And now we'll be interested in the second direction. Okay, I'm going to skip these two definitions. We have seen them before. One is the RK, where you have a fixed program, and it outputs the string with high probability. And the second is PK, where first we pick the randomness, then we pick the program. Here is the former result, the equivalence. So one-way functions do not exist if and only if an average case version of SOI holds for PK poly. So more precisely, if we can invert one-way functions, then we can establish the SOI inequality for most pairs XY coming from a polynomial time sample distribution. Okay, so that's the interesting direction for us. That on the one hand, if we had average case PK poly SOI for PK poly, then we can break one-way functions. But now we can also show the other direction. If you can break one-way functions, then we can prove this inequality for most pairs coming from the distribution. Okay.
The two t's are not the same, right? That was just
Yeah. So the question is why we have the same t's on both sides of the inequality. And it turns out that once you move to the average case, this poly t and t, it's not an important difference. Okay, so one-way functions do not exist if and only if for every polytime sampleable distribution, we can show the SOI inequality for most pairs in the input. Okay. And for the experts, the proof is robust, and you can switch the quantifiers here about how hard is the function on different input lengths and so on. Okay, but we won't be discussing these technical details from now on. Okay, questions about this, the main statement? Okay. So, so what's the interpretation? So as I mentioned before, one-way functions are really the holy grail of crypto. So they're equivalent to most of the basic primitives we would like to have. And this equivalence is telling us that failure of symmetry of information for a non-negligible number of pairs from a sampleable distribution is all we need to actually build one-way functions. Okay? So we want some polynomial time process that generate pairs of strings witnessing a failure of symmetry of information. So it's this break of the information between x and y that allows us to design one-way functions. And this precisely captures the existence of such functions. Okay, that's the theorem for pk poly. That's the clean result. Everything holds in the polynomial time regime as you would like it to be. We can also show an equivalence for rk, for this different notion of probabilistic complexity. But here, unfortunately, what we have right now only holds in the quasi-polynomial time regime. So we need to consider one-way functions secure against quasi-polynomial time algorithms. And we establish an equivalence to SOI for time bounds that are at least quasi-polynomial. And the overhead term here will become polylog n. Okay, so we have an equivalence, but it holds in the quasi-polynomial time regime. And it will be very interesting to extend this to polytime regime, but the techniques we use right now, they cannot do it. Okay, so I'll tell you now about the proof of the first result for pk. So here's the map of the proof. And as I mentioned at the beginning of the lecture, we can actually establish equivalences to other key principles such as language compression and coding, a form of coding. And what I'm going to do is I'm going to focus on these red arrows, these implications during the lecture. And the direction of breaking one-way functions from like SOI from the other principles is not very different from what I have already sketched here. Okay? So the focus will be on the red arrows. And to start off, I'd like to explain to you an equivalence between symmetry of information and what we call conditional coding. Okay? And this equivalence is going to be proven in the average case. So once we establish that these two principles are the same, we're going to get back and talk about one-way functions. Okay? So let's talk about coding. So we discussed yesterday this principle, which is if you can sample an object with some probability delta, then it has a description of length log 1 over delta. So that's a result from the time-unbounded theory. And we don't have such theorems for the original KT, the deterministic notion, in the time-bounded setting. But we can establish it for the probabilistic notion pk, as we saw yesterday. Okay? So just stating again the theorem from the last lecture. So if we take any polytime sampleable distribution dn, and we take some x, then we can code this x with respect to pk with complexity log 1 over the probability of x. because that's the time-bounded version of coding for PK. And we will need to use another result that complements this inequality, which is the following. You can code any element from the distribution with this complexity, but at the same time, you cannot do much better for most elements, okay? So there is a counting argument showing that for any distribution, D, it doesn't even have to be polytime sampleable, with high probability of oversampling an element from D, its Kolmogorov complexity is at least log 1 over probability of X. And if you put these two inequalities together, because K can be less than PK, and it's never larger, we get that for every polytime sampleable distribution, the PK poly of a typical string is roughly log 1 over the probability of X. Okay, so we can think of a typical element X from the distribution as having PK complexity log 1 over D and X. Okay, this is going to be useful for what's coming next. Any questions so far? Okay, let's go on. Okay, now introduce a definition. Okay, it's called conditional coding, and it will be the analog of that theorem if you talk about conditional probabilities and conditional PK complexity. So here's the definition. We would say conditional coding holds for PK if for every polytime sampleable distribution and every pair, X and Y, so notice that now we're sampling from pairs of strings, then I would like to say that the PK poly of X given Y is at most log of 1 over the probability of X given Y. Okay. So this will be the analog statement for conditional distributions and conditional complexity. Now, one way you might want to try to prove this is in the following way. Suppose I could just sample from the distribution of X conditional Y. Then I'll just apply the previous theorem. And then if I just give Y as advice, then I should be able to get a bound of PKX given Y. Okay? So that's perfectly fine, provided that you could efficiently sample from dx given Y. But in general, this can be a very difficult problem. Okay? If you have a distribution and you take some prefix of the distribution, can you sample now from the conditional distribution given that prefix? And that's closely related to this idea of Solomonoff induction and so on from time-bounded Kolmogorov complexity. Okay, so this can be a very hard problem.
The prefix could be f of x and the suffix could be x, right?
Yes, for instance, yeah. Okay, so it's not clear whether this holds unconditionally, and most likely it doesn't, okay? But this is just a definition, so this will be conditional coding for PK. And we can also consider the average case extension, where the statement says that for every polytime sampleable distribution, for most pairs, we have conditional coding. Okay, so there's a relaxation from worst case to average case. Okay, two definitions, worst case conditional coding and average case conditional coding. Questions? All right. Okay, so now I want to show to you a proof that average case symmetry of information, as we introduced before, to characterize one of the functions, is actually equivalent to the existence of average case conditional coding. Okay. So let's try to prove now this equivalence. So here is the here's the statement of average case conditional coding. Here's the statement for average case symmetry of information. And we want to show these two inequalities are equivalent. So to do that, let's just take a typical pair xy from D, okay? And let's focus on the inequalities we need to show. All right, so we have this pair, and we would like to show that this condition is equivalent to this condition here below. All right? Okay. So in both cases, we care about complexity of x given y. So let's just rewrite this inequality below in this way. So just moving sides. So now we want to establish this equivalence between the two inequalities. And the first thing we do is we rewrite this conditional probability using the definition of conditional probability, okay? So probability of x given y is just the probability that you get the pair x and y divided by the marginal probability of y in the second coordinate, okay? Just applying definition of conditional probabilities. Okay, so we get this equation. And now we just simplify. We get these two logs. And now, as I mentioned before, for sampleable distributions, this term, log 1 over the probability, for a typical element, this is precisely pk. Okay? This follows by the coding theorem and this inequality from below that I mentioned. So with high probability over the sample, you get that this term here is simply pk poly of the pair, and this term here is pk poly of y, because the marginal distribution of y is also polynomial time sampleable. Okay? And everything we did here, we didn't lose any information, so you can also revert the inequalities and to prove the other direction. Okay. So that's the equivalence between conditional coding and average case symmetry of information. Questions about the proof?
The equivalence holds for worst case coding also.
Yeah, it's unclear. And
Only because the equality is only for the average.
yeah, so it was very useful to use the fact that pk poly is log 1 over the probability for most x's, and we don't have this in the worst case.
Oh, is that why the other two scenarios are not clear, actually? Is this the point where the other two equivalents? Because you had these equivalents and there was coding, but when it came to symmetry of information, there was only an implication?
Yeah, this might be one of the points where it fails, but possibly in the second implication that we haven't discussed, we would also need something new.
But if we here replace this dm by the universal distribution.
Okay.
It's somehow strange why complexity is universal, and log 1 over dn, you use some specific dm. So what will happen if we put universal one?
Yeah, in that case, for pk poly, you would get the equivalence, I believe. That for every x, pk poly x is log 1 over the probability.
Yeah.
But then it's no longer clear whether you'll be able to connect that to one-way functions. Because sort of like the distributions that are related to one-way functions won't be the universal distribution.
But it's a part of universal distribution, so if it fails for some specific distribution, it should also fail for universal distribution. So universal distribution contains a part for everyone.
In one direction of the inequality, you can also have domination, but it's not both ways. So yeah, let's take it offline. I'm not sure. Yeah. More comments or questions? All right, good. Okay, so now let's look at this, the missing implication from if we can invert one-way functions, how can we establish conditional coding on average? Okay, so this is what we want to show. So we can invert any candidate function. And now, given a polytime sampleable distribution D, prove that for most pairs, we can implement the conditional coding inequality. Okay? Complexity of x given y is at most log 1 over dx given y. Okay, that's what we want to show. And a key tool we use is the notion of extrapolation from Impagliazzo-Luby and Impagliazzo-Levin. And they show the following. So if you can invert candidate one-way functions, then you can efficiently sample from the conditional distribution for most strings y in the second coordinate. Okay? And as we discussed before, there was the barrier for actually reducing conditional coding to coding. Okay? So that's what we would like to do, to use this result to reduce everything to coding. So let's see how this is done. So here's a formal definition of extrapolation. So they prove that if we can invert one-way functions on every input length, then for every polynomial time sampleable distribution over pairs, and for every C, there is a randomized procedure called X, this is the extrapolator, such that with high probability over the marginal distribution over the second string, then the extrapolator will produce a distribution given y that is statistically very close to the conditional distribution for y. Okay? So for most y's, we have an efficient way of generating the conditional distribution. And this holds with respect to statistical distance.
What is the distribution meaning it will give you some algorithm which accepts a random input, random bit string?
No, it's a sampler. So the algorithm X is a sampler.
Okay.
So it generates a distribution that is statistically close to the conditional distribution. Okay, so we will rely on this powerful result. And now let's sketch the argument. So we're trying to do conditional coding. So we want to show for most pairs we have the bound. So we know that with high probability over the second coordinate, the extrapolator produces a distribution that is very close to the actual distribution. The extrapolator runs in polytime. So in particular, it gives us a polytime sampleable distribution. So let's call it d prime y. Okay? And we know that this d prime y is very close to the actual d given y. Now, because these two distributions are close in statistical distance, we can prove that for most x's coming from the conditional distribution, d prime of x is very close to the actual probability of x given y. Okay. And now we apply the original coding for polytime sampleable distributions using d prime, which is sampleable. And we get the bound pk poly of x is at most log 1 over d prime of x. And we give y to both sides of the inequality. Okay? So here we have a sampler for this distribution, and the original proof of the coding theorem survives with some advice. Okay? So that's the advice. And now because d prime of y is close to the actual value, we get precisely the quantity that we want, which is the probability under the conditional distribution. Okay, so that's the sketch of the argument. Questions about this proof?
And originally, this constructions of extrapolator was used for what?
Okay, so one thing, so there's a lot of there's a probabilistic argument behind this proof using hash functions, and This is sort of like a time-bounded version of Solomonov induction, in a sense. So you're giving like some prefix of a distribution, and now you can sample from that prefix approximately. So that's one. Yeah.
It's natural, but
yeah.
in this paper when it was introduced, it was introduced for what? It was a technical a tool for something.
I think one of the things they do with this tool, maybe
just to construct one-way functions.
Yeah. So they actually don't prove this explicitly in the paper. They claim this result, and the proof uses techniques very similar to what they are already doing in the paper. But I think one of the things that you can do is I give you a distribution and you want to approximate the probability of an element under this distribution. And similar techniques can also be used to do that. So if you can invert one-way functions, you can approximate probabilities of elements from the distribution, and also from conditional probabilities. And this is more like sampling from the distribution. So there is also this notion of distributional inverters, where when you want to find the pre-image of f of x, you actually want to find a uniformly distributed pre-image. So this is also useful for that.
Yeah,
so, yeah.
The original motivation was to consider a weaker notion of one-way function, where security is you don't want just to find a pre-image, but you want to find a random pre-image, like uniformly random pre-image. And they showed that the two notions of one-way functions are equivalent. And for that, they were able to show that you can sample a random pre-image if you know how to invert one-way function.
Yeah. So that's a particular case of. Yeah. Yeah, so that's a more restricted application of these extrapolators, but that's sort of like the most general form. Yeah. Thanks, Valentin. So more questions? All right. Okay, so that finishes the sketch of the relation between one-way functions and SOI. We first rephrase the problem by establishing an equivalence between SOI and conditional coding in the average case. And then we obtain conditional coding from one-way functions. Okay, so that was the proof. Okay, so now we would like to do the same thing for RK, which is arguably an easier notion to understand. You have like a fixed program that outputs with high probability your string. But a key difficulty here is that we don't have this unconditional coding theorem. Okay, that's a very interesting open problem, whether we can show it unconditionally for RK. And therefore, we need to use a different approach. So I'm only going to sketch the proof. So we would like to show now that if we can invert one-way functions in quasi-polynomial time, then we can prove SOI on average for RK with quasi-polynomial parameters. And the proof goes as follows. First, we rely on a result from Ilangoren and Santana, where they show that if you can invert one-way functions, then you can approximate the time-unbounded Kolmogorov complexity of x given y for polynomial time-sampleable distributions over pairs xy. Okay, so for most pairs xy coming from a polynomial time-sampleable distribution, you can approximate kx given y. Okay, and this connects to what Valentin was explaining earlier this afternoon, which is when you can compute different notions of Kolmogorov complexity, you can use these procedures as distinguishers. Okay, so we'll combine this with a PRG construction and this play to win or play to lose approach. Okay.
But here we have which kind of Kolmogorov complexity?
Okay, so here we have time unbounded. So this is a very powerful algorithm, right? It estimates time unbounded Kolmogorov complexity.
But it seems that the time unbounded Kolmogorov complexity is just difference between complexity of pairs and complexity of y. And each of, for most things, is just close to probabilities.
Right, so that's a very good point. So as Sasha was saying, kx and y, well, okay, so let me say that in two steps. So kx given y, because of symmetry of information, you can approximate this quantity if you can compute the usual Kolmogorov complexity with all conditional strings, right? So that's the SOI inequality. It gives a way of approximating this. if you can only compute like this quantity and this quantity, so you then can approximate this one. Okay, so this is sort of like just a simple extension. Now this K is connected to probabilities because of coding theorem for K, for time unbounded. So if you can estimate probabilities, then you can sort of like estimate K. So that's the intuition, yeah. Yeah, thanks, Sasha. But yeah, let me not say anything more about the proof, okay? But that's sort of some intuition for it. Okay, so we have a distinguisher, and we're gonna use a convenient generator whose reconstruction gives RK bounds, okay? And when we put together this distinguisher with this generator, what we'll be able to show is that for most pairs of strings from a sampleable distribution, the RK complexity of x given y is at most the K complexity of x given y plus some lower order term. Okay, so you get this, this result. And this is really the central inequality that explains everything I've been discussing so far. Because RK, you have just shown to be at most K, so that's very non-trivial. Of course, K is at most RK, right? So K is time-unbounded version. So therefore, you collapse RK and K for most pairs coming from the distribution. So now you know RK is essentially K with high probability, and we know SOI holds for K. Therefore, you get SOI for RK as well. Okay, so that's the approach and the second proof. And it sort of explains why you get all these equivalences once you can invert one-way functions, right? Because now K and the time-bounded measures, they collapse. And now the properties of Kolmogorov complexity, they survive in the time-bound setting, at least on average. Okay, so that's the intuition.
So the quasi-poly is just on that arrow, the first one?
Yeah, the quasi-poly, this implication also holds in the poly regime. Unfortunately, this generator, you have to pay an overhead that becomes quasi-polynomial time. So we don't have a reconstruction with RK that will give you optimal bounds.
Oh, you only have it for PK.
Yeah, we only have it for PK. Yes.
So if you replace D by like simple uniform distribution, then all this becomes much simpler.
For uniform distribution, just complexity is 2n and n.
Yeah, I guess.
If instead of samplable you take a uniform, then everything simplifies.
Yeah, everything will be close to n. Yes, yes. Right. More questions, comments? Okay, so still have a few minutes. So now let me tell you about the more general theory. So I explained to you the relation between one-way functions and these different notions. I mentioned we also have equivalence for the worst case complexity of NP. Here there's a gap, so we don't quite understand the role of SOI. We can show if NP is easy in the worst case, then you can prove SOI for all pairs. So this is the worst case version of SOI, the usual one. And even with weaker assumptions, we can get this. So that's what Valentin explained in his talk. So if you can compute MKTP, which is a probability in NP on average, then that's enough to get SOI for PK. But what we are doing here when we study one-way functions is much weaker in the hierarchy of assumptions, okay? So by inverting one-way functions, it's not clear whether we can solve NP problems on average, okay? So there's some gap still to understand the relation between worst case SOI and the usual computational assumptions. And we also get characterizations for the easiness of NP on average. If you're not familiar with these different notions of average case complexity, so the heuristic inclusion is when the algorithms for your NP problem can make two-sided errors. So you correct with high probability, but you can make some small number of mistakes. In this definition here, you have 0 error. So you either say, I don't know, or you give the correct answer. Okay. It's also an interesting problem whether we can prove worst case SOI if in the initial assumption you can make errors like on both sides. So we also don't know the answer to this question. So I just want to state to you the equivalences in this case, because it uses a sort of mysterious notion of, we call it independent average case coding and independent language compression. So let me explain to you just the statement of these results.
Yeah, but sorry.
Yes.
Can you say again?
Yeah.
What is conditional language compression? What is just language compression?
Sure. Yeah. Let me show it to you. Okay. So these are all the notions. So this is the one we discussed so far, the average case conditional coding. And this is the natural one, the worst case for all pairs. And what I'm going to introduce next is what we call independent average case coding, or conditional coding.
Yeah, but for language compression.
Oh, you want to know for language compression? Okay.
Green thing.
Okay. So we're discussing language compression in the conditional setting. So you have a language over pairs, and you want to code the elements in the first coordinate for a given element in the second coordinate. So you look at our string x such that xy is accepted by L, and you want to code with respect to the size of Ly. Okay, so that's what we mean by language compression here. Does that answer your question? Yeah. Okay. Okay, so I'm going to introduce now these independent variants of these statements. So let me go back to the slides. Okay, so here's the theorem. So NP is easy on average with two-sided error if and only if we can establish independent average case conditional coding for PK poly.
Sorry, what's heuristic ECG?
Yes, so. Okay, so given some language L, let's say in NP, and given some distribution D, let's say P sampleable. So we're interested in algorithms with the following property. When you take some x from the distribution and you give to the algorithm x and some parameter k, then the probability that you make a mistake is at most 1 over k. Okay, so it's the problem is easy on average, but you can make mistakes. For most inputs, you don't make a mistake. Sometimes you make mistakes. And so dist NP is the class of all pairs L, where L is the language in NP, and D is some polynomial time sampleable distribution. And that inclusion is saying for every such pair, we have an algorithm of this form. So it can also be randomized. And this is polytime. Okay, so we have, you can solve the problem on average in polynomial time with respect to any polytime sampleable distribution. Is that clear? Okay, and the equivalence says the following. So we consider again conditional coding, but the only difference is that before we had a single distribution D over pairs, so we would sample x and y from D. Now we have two distributions. They don't need to be related at all. And you sample y from the first distribution C, and then you sample x from D conditional on y. Okay, so now you decouple x and y, and you have two distributions. One tells you what is the second coordinate, and then you sample from D according to this y in the second coordinate. Okay, so this is a more general statement.
So this is harder to do.
It's harder to achieve this because it works for a larger class of distributions.
Because I could always take C to be the marginal.
Yes. Yeah, and this is what you would expect, right? Because
If you can take C the marginal, but why the D is not sampleable then? Could be.
no, only D is sampleable. The statement doesn't say that D given Y is sampleable. And that's important, yeah. So here D is any sampleable distribution over the pairs, and C is sampleable distribution over a single string.
Yeah,
Okay.
So it's incomparable somehow.
It's more general, because you could just let C be the marginal.
But then conditional distribution, is it sampleable always?
Well, the statement doesn't say the conditional distribution of D is sampleable, only that D is sampleable. The marginal is sampleable.
Yeah.
Yes. Yeah, and the reason why I would expect to get something stronger is because of this hierarchy, right? So before we could invert one-way functions, now we can solve NP problems on average in polynomial time. So at least we hope to get something more.
Just on the top. So D, so the converse is, X over Y, that's over D. So the role played by C is just.
It's quite strange. You take some sampleable D, then you get some conditional distribution, and you combine this conditional distribution with arbitrary distribution on the second component.
Yeah. Yeah, maybe I can try to give some intuition for why you might expect something like this. Or I'm not sure I can give the intuition, but so when you think about one-way functions, what you're doing here is you're sampling an instance and also sampling a solution at the same time. So you have x and f of x. So that's the same distribution. So you're generating hard instances with a solution, except you don't reveal the solution to the adversary. Okay. Now, when you talk about NP versus like average case, so you're only talking about like sampling some distribution of hard instances, but you're not sampling them with solutions. So think about like you're sampling some SAT formulas, but you don't know the satisfying assignment somehow. So in one case, you have some coupling between these two, but for NP, you don't. So and that's sort of why you would need like something else here to get the equivalence. Maybe you can think of Y as being like like C is generating SAT instances, and D is generating a pair of like satisfying assignment and an instance. And you're sort of trying to link the two now. Yeah, I'm not sure that gives an intuition, but that's sort of why we have this. More questions? Okay. Okay, so open problems. Yeah, I think the most interesting open problem is to get a better understanding of SOI and time-bounded Kolmogorov complexity. Is there any computational assumption that precisely captures worst-case SOI? We still don't know that. We have some implications, so we can sort of like restrict a little bit the kinds of hypotheses that one might hope to have, but there's still a gap. And finally, we saw yesterday, we also saw in Valentin's lecture, this connection between worst case and average case complexity that goes through Kolmogorov complexity, right? So perhaps this equivalences between questions in complexity and results in Kolmogorov complexity can be used for like different results. And I think it's worth exploring these equivalences to see what else we can prove. Okay, So the main reference is this paper, and that's all I wanted to say. Thank you.